Oh, not again.
Picture a nice day in the late Cretaceous about 65 million years ago. In one area, a friendly T-Rex is out looking for food. Somewhere else, a herd of duck-billed dinosaurs are socializing around a watering hole. Nearby, a group of Triceratops are spending some quality time together. Unknown to them, a large asteroid, 10 kilometers in diameter, is zoning in on a location on the Yucatan Peninsula, moving at a velocity of 50,000 miles per hour. As the asteroid begins to enter Earth's atmosphere, the dinosaurs start to run in fear, but it is no use. The impact of the asteroid has a strength of 300 million nuclear bombs, immediately exterminating anything within the immediate distance. Within a week, a dust and debris cloud will be stretching out in all directions from the impact site at a size of 4,000 kilometers. As the second week begins, dust and soot begin to travel around the world, creating worldwide effects. By 4 weeks after the event, a large dust cloud will have engulfed the planet, causing permanent night for months. This dust cloud will lead to a global winter lasting for 3 years. As the years go on, more and more species continue to die off until 80% of species on Earth are wiped out. 10 years following the event, a large crater is left on the Yucatan Peninsula with a diameter of 180 kilometers. It would take 65 million years for a father and son team of scientists to find this crater and tell this story.
The Alvarez hypothesis posits that dinosaurs went extinct because of a meteor impact. This hypothesis is named after father-son Louis and Walter Alvarez. Louis Alvarez was a Nobel Prize-winning physicist, and his son Walter was a geologist.
So he said, well, as a matter of fact, we have a job that I think just fits you. Because normally when you develop a new weapon, like a new bomb or anything of that sort, new rifle shell, you take it out to Aberdeen testing grounds and you test it and test it.
My father got busy, and the things that physicists love to do, I would hate this, but he loved it, was to make a special iridium coincidence counter that made it possible to measure lots of samples real fast, you know.
Together, Louis and Walter came up with the Alvarez hypothesis and were the first to discover the KT boundary on a trip to Italy. A lot of evidence needed to be found to prove the Alvarez hypothesis. They needed to find a crater of the right size and age, worldwide boundary clay at the KT boundary. They had to find worldwide effects. They needed evidence of an impact such as shocked quartz and spherules, and to prove that iridium is rare on Earth's surface and the iridium at the KT boundary is caused by an impact, not by the environment. Louis and Walter were able to identify the KT boundary in Italy. The boundary contained a clearly visible layer of clay as would be expected with an impact. This clay layer can be found all over the world. This clay layer at the KT boundary contained 30 times more iridium than is typically found on Earth's crust. As you can see on this graph, where depth is shown on the y-axis and amount of iridium is shown on the x-axis, there is a major spike in iridium levels at the KT boundary. This is evidence for an impact because meteors are known to contain a lot of iridium. There is also evidence of worldwide effects from the impact. Charcoal and soot have been found as evidence for massive forest fires around the world. These fires were caused by extremely hot impact debris that rained down around the world. A worldwide boundary clay is also evidence of worldwide effects, as well as worldwide evidence of extinction. Lastly, evidence for the Alvarez hypothesis is the Chicxulub crater found at the Yucatan Peninsula in Mexico.
Thought to be the remains of the impact that killed the dinosaurs. Cratering is common on Earth and in the solar system. Fewer craters remain on Earth today because of erosion and weathering. Craters can be broken into two different classes, simple and complex. Simple craters have bowl-shaped depressions and are typically crater-formed structures on the Moon with rim diameters of less than about 15 kilometers. Complex craters occur on the Moon for those that are greater than 15 kilometers in diameter. These have shallow, relatively flat floors, central uplifts, slump blocks, and terraces on the inner wall of crater rim. In even larger craters, such as 20 to 175 kilometer diameters on the Moon, the central uplift is typically a single peak or a small group of peaks. Even larger, such as greater than 175 kilometer diameter on the Moon, have complex ring-shaped uplifts. When larger than 300 kilometers, these are termed impact basins and not craters. The material ejected from a crater is deposited mainly in the area surrounding the crater. Closer to the crater, the material forms a thick, continuous layer, but at larger distances, ejected can be discontinuous clumps of material. Some of this material ejected is large enough to create a new crater when it impacts. These are termed secondary craters and typically occur as lines of craters pointing back to the original crater. Material below the surface of the crater is disrupted by the shock of the impact event. Near the surface is a layer of breccia, which is coarse, angular fragments of broken up older rocks. Rocks at deeper depths remain in place but are highly fractured by the impact. The amount of fracturing decreases as depth below the surface increases. The energy of impact typically causes some material to melt. In small craters, impact melt occurs as blobs of material in the breccia layer. In larger craters, impact melt may occur as sheets of material. The Chicxulub crater itself is a buried 180-kilometer diameter crater on the Yucatan Peninsula that is the impact crater from the KT event. The size and shape are revealed by magnetic and gravity field anomalies and oil wells drilled in and near the structure. The stratigraphy of the crater includes a sequence of andesitic igneous rocks and glass interbedded with and overlain by breccias that contain evidence of shock metamorphism. Andesitic rocks that have chemical and isotopic compositions similar to those of tektites found in the KT ejecta. There's a 90-meter thick KT boundary breccia that also contains evidence of shock metamorphism, which is present at 50 kilometers outside the crater's edge. The breccia probably represents the crater's ejecta blanket. The KT boundary age is indicated for the age of the crater. The crater is in a thick carbonate sequence, so shock-produced CO2 from the impact may have caused a severe greenhouse warming. Seismic data collected across the offshore portion of the impact crater determined that the diameter of the transient cavity is around 100 kilometers. This is critical for constraining impact-related effects on the Cretaceous environment. Previous estimates of the cavity diameter span an order of magnitude in impact energy. Offshore seismic data indicate that the Chicxulub crater has a multi-ring basin morphology.
Oh, goody! An earth creature!
Is such a thing even possible? Yes, it is.
Mapping techniques such as 3D modeling and geographic information systems, or GIS, allowed scientists to create a digital map of the Denver Basin. This map helped determine where outcrops lay in relation to each other, as well as providing a more accurate way to date found fossils by seeing where they lay in reference to the rest of the basin. It was this mapping that helped determine a site for the core to be drilled. The Kiowa core was drilled in 1999, between March 1st and April 16th. Kiowa, a small town in Colorado, was chosen as the location for the drill site due to its proximity to the center of the Denver Basin. Sponsored by the Denver Museum of Nature and Science, this project cost about $110,000. The goal, as stated by Reynolds and Johnson, was to obtain a stratigraphic record in fine-grained strata from the center of the basin that would provide a high-resolution paleontological and paleomagnetic record of the basin-filling strata. By the end of the 2,256-foot drill, that goal was met. Not only was 93% of the core recovered, but it became the most widely known core record, as it provides a very complete story of the layers retrieved beneath the basin. The Kiowa core serves as a key for calibration of the geologic studies of the Denver Basin. It is often used for the analysis of sedimentology, palynology, isotope stratigraphy, magnetostratigraphy, petrography, thermochronology, and and sedimentary provinces. But the stratigraphy was not the only thing discovered. The KT boundary was pinpointed using the Kiowa core sample for the first time. The KT boundary was found in the Kiowa core using palynology, magnetostratigraphy, and the presence of anomalous iridium and shocked minerals. Using the 3D basin model mentioned before, the KT boundary was projected onto the surface where it was discovered in another place for study, the West Bijou Creek Escarpment.
Okay.
Okay, ready
Okay.
now.
Yeah.
As stated by Reynolds et al., the West Bijou Creek section is the most complete terrestrial KT boundary interval known. It is characterized by a full suite of KT boundary indicators, including palynological extinction, the iridium anomaly, a shocked quartz anomaly, a fern spore spike, a carbon isotope excursion, reversed polarity, late Cretaceous vertebrates and plant megafossils below the boundary, and early Percan mammals and basal Paleocene plant megafossils above the boundary.
Abundance of fossil plants during the Cretaceous and Paleogene that can be seen in the Denver Basin has been known for over a century. People slowly began to collect these fossils, but they failed to take note of which stratigraphic level they came from. Eventually, scientists began to take notice, and it was soon realized that the fossil leaves are the most abundant conspicuous fossils in the synergetic strata of the Denver Basin, making them useful for dating the rock layers. A problem dubbed the layer mine problem began to develop because new leaf data seemed to conflict with vertebrate and invertebrate fossils, making finding the exact KT boundary layer hard to find. A team of scientists were eventually able to correlate the two to identify the level where the KT should be. In 1939, scientists found the first section of the KT in the southern corner of the South Table Mountain in Golden, Colorado. Using the geologic structure of the basin and selected fossil sites, it was possible to estimate the position of the boundary throughout the surrounding basin. Following the creation of the Alvarez hypothesis, scientists were able to locate more sections of the KT boundary. In 1986, a boundary site in southwest North Dakota showed high levels of paleoformal and megafloral extinction at the KT boundary. Today, the best preserved KT boundary site is located at the West Bijou site, located in the Denver Basin. Fossils found at this site allow for assessment of early Paleocene patterns of plant diversity. 4 meters below the boundary clay, a Hadrosaurian dinosaur fragment. Fossils found at this site allow for assessment of early Paleocene patterns of plant diversity. 4 meters below the boundary clay, Hadrosaurian dinosaur fragments were found. And 12 meters above the boundary clay layer, diagnostic basal Purican mammal jaw fragments were found. This shows the change from dinosaur to mammal dominance after the KT extinction. Okay, stop. 9 leaf localities at 8 stratigraphic levels in the basal 22 meters of the Paleocene section were sampled and analyzed to better understand the flora that survived the global KT catastrophe. The Paleocene flora of the site is taxonomically dominated by dicotyledonous angiosperms at 74%, lesser numbers of monocotyledons at 10%, terms and alleles at 11%, conifers at 5%. By number of specimens, angiosperms comprise greater than 95% of the flora. Within the sampled section, there are no recognizable directional trends of diversity or abundance, suggesting the earliest Paleocene vegetation was stable, although not.
God damn it.
And I can't say directional.
Alright, are you ready? Palynological. Damn it. What is.
In 1986, a boundary site in southwest North Dakota showed high levels of polynormal. It's so hard to read.
Megastratigraphy. Fuck.
Does it look good?
Yeah, but your hair is gonna tell. Petrography. Hold on, I gotta say these words. Petrography, thermochronology, and sedimentology. Alright, we're ready.
Jesus Christ.
No, and we're not putting that in bloopers.
Stable, although not particularly diverse.
Fuck. God.
Exact KT boundary layer. Can you stop?
But the stratigraphy. Fuck. Alright, good. We at least got through that.